I'll be talking about the data extraction, pre-processing, feature extraction, and database layers of our project. For the data extraction, we are using three sources. The first two, YouTube and Hacker News, are used to gauge the informal sentiment of the general public, while the last one, research sources, is used to gain formal insights from people who are knowledgeable on this topic. Here's an example of a file in the data extraction layer that is responsible for fetching YouTube transcripts. As you can see, it fetches the YouTube transcripts and saves the valid ones as a JSON file. Here is the saved JSON file. The output of the data extraction layer is used as the input for the pre-processing layer. The pre-processing layer has the following architecture: a utility file that contains all the pre-processing functions that would then be used by these pipelines, and these pipelines would be run by the central pre-processing RNO file. Here's how it works. We got the utility functions over here that are important for pre-processing. Then we got the pipeline. It defines the route, uses these functions, and returns a JSON file as an output. And then there is the file that is used to run everything. Here's an example of a clean JSON file. These files will be used as the input for the feature extraction layer. The feature extraction layer has a similar architecture to the pre-processing file. We got our basic utility functions over here, then we got our models. The bird topic model is responsible for topic modeling, the keyword model is responsible for keyword extraction, the rebel model is responsible for finding relations, the spacey model is responsible for named entity recognition, and the radar model is responsible for sentiment analysis. As you can see here, these models are fully defined and then only utilized by these pipelines. Here it is, similar to the pre-processing, just routing the paths and running the function, and then all of these pipelines are centrally run by this command file. Here's an example of a file with its features extracted, specifically the research topic results file, and these files are used along with the pre-processing files as inputs for the database layer. Our database layer consists of two databases, a structured database and a vector database. The structured database is responsible for exact match filtering on known fields. It provides the RAG with this function, while the vector database provides the RAG with a semantic similarity search. The DB folders contain at least three files. The schema, the file that is responsible for transferring information into that schema, and the output. Here is what the structure schema looks like. It is really large because it contains information from both the feature extraction files and the pre-processing files, while the vector DB is much smaller. The vector DB is much smaller. As you can see, there are only 3 tables in it, for the 3 data sources. Additionally, the vector DB utilizes chunking, which is essential since the vector database cannot process an entire transcript. And just like the last 2 layers, the database layer contains an execution file that executes the entire layer and produces the results. Now, you might be asking, why did we use SQLite instead of VV8? The reason for this is simple. Our project is small enough that we couldn't justify using the more complex system of VV8, and instead chose the more lightweight, serverless SQLite. This is all for the database layer.
Hi, I'm Salman. Now moving on from the database layer, I'll be talking about the RAG and the orchestration part of the project. So first, this is the RAG folder. This is responsible for taking the user's question and finding the most relevant information from the data we stored earlier. So the retrieval, we have different retrieval files. Each file is responsible for a different type of searching. This is the metadata retriever. It's used for when we want to filter by information like the source, sentiment, topic, correlation, stuff like that. This is the semantic retriever. It's used for similarity search. So even if the user does not want to use the exact same words as the data, it can still find relevant chunks using embeddings. Then there's the lexical retriever. It's more keyword based. This is useful when exact words like water, energy, data centers, or company names and stuff like that. Then there's the hybrid retriever. This combines both lexical and semantic retrieval, so we are not relying on just one search method. Okay, we go to prompting. To retrieve the documents, we use the prompt builder. We use a prompt builder. This file takes the retrieved documents and formats them into a proper prompt for the LLM. This is important because the LLM should answer based on the retrieved context, not just random information. Then here we have the templates. We have templates for normal questions. We have templates for like some summarization and like sentiment insight. Now I'll be moving on to the next layer, which is agentic orchestration. This layer like connects the RAG system with the LLM and like controls the flow. Here's a query planner, decides what type of question the user asks. For example, if it is about sentiment, it can use a sentiment prompt. Otherwise, it can use like the normal QA prompt. And we have the graph. The graph file contains the main flow. It routes the query, retrieves the documents, builds the prompt, and generates the answer, and then like checks if the answer is grounded or not. Then we have the LLM client. This is where like the model connections handled. Our project supposed like two models. There's like the small model and like the big model. So it's like a small model for like routing and checking, and a bigger model for like generating the final answer. Then finally we have the run agent.py. It's what ties everything together. It's what the app calls when the user asks a question. So overall, this section takes the data from the database layer, turns it into a working question answering system. It receives the source, builds the prompt, calls the LLM if it's needed, and returns both the answer and the evidence. The next part, I think, is the user interface and tracking with Streamlit and MLflow.
Now, moving on to the user interface and system tracking, we use Streamlit for the app and UI development and MLflow for the system tracking. I'd like to also point out that we created a script to run the MLflow UI instead of actually using the basic MLflow UI command, because it opens the MLflow with our project's correct SQLite backend and the artifact folder. Now, for our app, we just have a simple UI design. As you can see, the user is first presented with 3 questions they can ask directly. And if they have different questions, they can just simply type their question and send it over. On the side, we have a sidebar that contains features like creating a chat, checking the database status, customizing our retrieval settings like using specific retrieval strategy, and the amount of documents you want retrieved. We can also customize our generation settings, and there's also information about the MLflow port and how to access it. Now, moving on to the MLflow, we have the 2 experiments, which are the drift and the RAG experiments. Let's talk about the RAG. Each run basically saves a question from the user and the answer for that specific question from the agent. Now, the metrics that were saved are latency seconds, like how long it took for the agent to answer, the number of source documents, number of sources, answer length, etc. Now, for the parameters, it's the settings that the agent used to answer this question, like the retrieval strategy, the top K, and if it did use an LLM or not. Now, for the drift experiment, we have a drift detection system. We have 2 types of runs. We have the baseline creation and the drift check. For the baseline, we have basically when the model was stable, the metrics for that model, basically all the information for it, and then we have specific parameters. Now, for the drift checks, we compare the current model stats with the baseline and output a specific percentage of change. If the percentage of change is high enough, then we'll get alerted, and here are the specific parameters for it. Now let's test our system. Let's suppose we want to ask it to summarize the research on AI energy consumption. Let's just use an auto retrieval strategy, maybe change the top K to 6 and use LLM. We can go ahead and ask the system a question. Now what's happening is it's using a specific retrieval strategy where it retrieves 6 documents. It passes these 6 documents as context for the LLM, and the LLM generates a response. Now all this information gets logged into the MLflow, like the parameters used here and how long it took the AI to answer our question. As you can see here, this is the response of the LLM. It took these specific sources. We have multiple sources over here. It took these sources as context and gave us this answer. Now let's look at the MLflow, refresh, check the RAG system. This is our specific query. Let's open it and look at our metrics. It took us around 11.42 seconds for the agent to answer. This is the number of K. This is the K number we saw previously, the answer length, prompt length. And now on the parameters, as you can see, it shows us the specific retrieval strategy it used, our query, the top K, and if it used an LLM or not, and extra information about the system. Now moving on to the drift detection, we have 2 things we can do. As we said before, we can either create a baseline or we run a drift check. To create a baseline, we first of all need to write the name of the file and then chase it with a -- create baseline. If I want to override the one I already have, I add a / force, but we keep the one I already have. Now, to actually run a drift check, we just run the file normally, and we wait for the system to take a snapshot of our current model for comparison. Now that the drift check is done, we can see that there was actually a noticeable drift in the retrieval drift. For more information, now we'll move on to the MLflow UI to check the metrics. Now that we've done the drift check and we've noticed that an alarm was set, we can look at the metrics and check what caused it. And turns out it was the retrieval average latency, because this specific question that we asked did take a lot of time for the system, for the rack system to actually retrieve the sources. It took more time than usual and sort of the alarm, but other than that, the system looks perfect.